Hello, everyone. This is Lab 7. We are going to explore what is temperature. You all have thermos. You talk about the temperature, it's cold or hot, and what is temperature exactly? And we use the ideal gas model to explore what actually temperature means physics-wise. Okay, we know that when things get hot or warmer or hot, the atoms and molecules within them move faster. But how much faster? To answer this type of question, we must have a scale of measurement, with some kind of calibration. This lab reviewed to students the relationship between the kinetic energies of the particles and the temperature. And in particular, we're going to use the simulation from this site. You double click this, then you will see here. And the gas properties, we will use this for a number of labs. But the first one is we can click energy. And what we have is a container here. So, and simulate, and we can pump into some molecules, and the one I want you to do is with some certain temperature. So then you can see inject temperature 50 degree Kelvin. Okay, now you know the temperature can have Fahrenheit or Celsius, and as we learn from physical science. But then here is another temperature scale called Kelvin. Actually, that's more often referred to by scientists or engineers. And this is Kelvin degree is also called absolute temperature. We will learn more down the road in the class. So introduce with 50 degrees. And then let's pump in the gas about 100 or so like this. And so that's like a container. And we can heat up this system by turn on the fire underneath over here. Okay, the fire, and when the higher fire goes, and or we can cool down with the ice. Okay, and well, this is, and we have a thermometer over here and measure actually temperature in Kelvin, but you can switch to Celsius, how many degrees. Unfortunately, we don't have Fahrenheit, and later you will know how to convert between Fahrenheit and Celsius, Kelvin. So now we use Kelvin because it's directly related to the Kelvin degree is directly related to the kinetic energy of the particles. So then make sure this average speed is displayed here on the upper left corner, and the speed distribution. If you look into this, the molecule, you can see all these molecules are moving. Are they moving at the same speed or same directions? Or particular velocities, all of them are vectors. But no, and also they bump into each other and making collisions. So we talk about now, actually, imagine we zoom into a substance or gas, and they are bumping into each other. And this speed, some are very slow. See, that one is hardly moving. And this one goes real fast, and they all have different speed, and therefore, statistical-wise, we can say they have a speed distribution. Remember the word distribution means different speed. You count numbers at different speed. What plotted here is a speed distribution. So all these bars. So on the horizontal axis, the bar, okay, speed, and which is number of particles at the speed. Of course, this is just a qualitative plot, and we hardly don't even have the units. We don't even need units. But the higher more to the right, and the higher the speed. And on the vertical axis, on the speed distribution, and the number of particles at this speed. So number of particles, for example, at this speed is high, and on a high speed is less number of particles at the higher speed, and also less number of particles at the very low speed. And most particles are at average speed. that doesn't mean say everything is at the same speed. Okay, that's why whenever something has different values and you have millions of them, that's when you will have a distribution plot like this. It's called speed distribution. So I will ask a question about the speed distribution later in the lab. So then once you have that set up, you will see the speed at this moment is here, and then you will heat it up to say first temperature. I want to set the temperature at about 100 degrees. Once you cool it down with ice, you will see the temperature drop, and if you heat it up, you will see temperature go up. Okay, and at the same time you can just watch, and they are getting faster or getting slower. But on average, once again, it's on average is faster. Even at the highest temperature, there are still some out there moving very slow. But even at a very low temperature, there are still a couple of them moving super fast. But it's all, there's some randomness in this. So set at 100 degrees to begin with, and then you will read. So set at 100 degrees. Okay, and then you read it's okay. Average speed at 100 degrees is say 263. See, you wait for a few seconds to make sure it's stabilized, but they will never stay the same. Why? Because that's the nature of random motion. Okay, with large particles, all randomnesses, and if you do even the average, it's called fluctuation. You know, it's always, that's the nature of microscopic system viewed macroscopically. So then you say, well, at 100 degrees and the speed is this, and then what I want you to do is to insert that into this table, say 100 degrees, and then you would repeat this process. Then you adjust it to 200 degrees. Okay, and you put into 200 degrees, and then you adjust this, give some fire, and it will go to 200 degrees. And well, you try to do as accurate as can, but it always gives some time for this table to stabilize. Then you see the nature, random nature, or people call it stochastic or random. Okay, but it's always a fluctuation, but there it is. So the 200 degrees now, and then you have 360. Just read your best. You have to take average over here by eyeballing. So okay, so is it going from? I see going from 9 to 3 or 380 or 375, and then enter 200 degrees over here. So 200 degrees over here, and then keep going in this, and 3 to 400, and then you're probably tired of it, and then you go 200 degrees at a time. So 800, 600, 800, and then after that you go to 1,000, and then you go 1,500. You increase by 500, and then go another 500, and then another 1,000. So then you have this column fills up. In fact, I have down here examples at the bottom. I have the data similar. Don't copy these numbers. You have, because this number I did on purpose. You will not get exactly this number because it's fluctuating. Okay, so you fill this up. So then you answer these questions. As temperature increases, the molecule move obviously faster. Sketches speed distribution. That's this type. Don't copy this one. You draw by hand. You use some of your computer skill, cut, paste, and insert it over here. And 100 degrees. And do the same for 1,000 degrees. Okay, and do the same for 1,000 degrees. Okay, and let's see. You compare to them. Can compare the distribution. Just get the idea, the distribution. And then here I ask you the question about sketch this, and then at 1,500 degrees, are there still some molecules moving very fast, very slow? When higher, now when the temperature is higher, it's moved faster. But then I ask, Well, it's very high temperature. Are their molecule move at a very slow speed? Well, the answer is yes or no. So I will ask you. Okay, but since this is a lab and it's an observation. And the second part of this is doing some analysis. Assuming you have one column, this requires you to use Excel. And in fact, if you nowadays everything is computerized, and the Excel skill is very important no matter what subject, what discipline your career will be in. So the task to do is make a enter the data into Excel. So I have a video demo there you can watch. I don't want to repeat that. So you can see how to do that. But then you enter like this. So enter into Excel and these two columns into the, and then so that's the first step. And then compute the squares. Why do I compute the squares? We will talk about the theory. So then temperature is related to kinetic energy squared, half kinetic energy, but now see there's a bar over there, square and take the average. So that's the kinetic energy. That's a very small number, okay, for each one of them. But they are still different, like average kinetic energy, that's in the system. But then that is related to temperature with this relation. So here, don't go to the math yet. Then the temperature actually equal to these numbers, kinetic energy. And then, but you think about the kinetic energy of a particle over here. The particle, kinetic energy of a particle is very small, okay? But that's the scale of temperature. Therefore, physicist, actually Kelvin, put a small divide by a small constant, so that makes this number reasonable, okay? So then that's exactly the formula. So then that's part of kinetic energy, and that's EK. So we're not getting to this yet, but we just get to the trend. The kinetic energy of average is very small, but it does difference, and it relates to the temperature. So actually, temperature is average kinetic energy. Oh well, multiplied by a constant. Okay. So then you compute that. Since kinetic energy related to speed squared, I will compute the squares of this. Compute the squares of them, and then enter into the Excel column, as well as the, so then the idea here is for 100 to 63, that's the speed, and the square to 63 is 69169. That's the first column. And then if you calculate 375 squared is 140,625, second column, and so on. But good thing that with Excel you don't have to calculate one by one. There's a video here's a video I talk about how you do that, and that's a good skill. And this one, in fact, you can do any function with transform one column data to another form with some given procedure you want to do. So you can automatically do this. So that's the second step. And then of course, once you have that, and then you make a graph. So also in a video, speed versus temperature graph, and actually it's over here, this one, speed versus temperature, and then looks like it's a curve, okay? And so then make another plot, and once you have the square, and then make a speed squared versus temperature plot, and insert a snapshot here like I do. So that is required. Yeah, make it insert here. So then when you're done, you can delete mine and insert yours. And then next one, and for the two graphs, then there's a question. Which one looks more like a straight line? Of course, I will ask you. And then this question, true or false? Mathematically, a straight line will indicate a linear relation or proportional relation, and that's true. Okay, which means if you see a straight line, actually the kinetic energy squared, and that's speed squared is actually proportional to kinetic energy. If you average that, and you will see a straight line, the temperature and the average kinetic energy is a straight line relation, which means it's proportional, and that in fact that defines the temperature. So in fact that temperature defined, that's a, you can say a special temperature for now, and that's physics temperature. This is called a Kelvin degree temperature. So Kelvin degree temperature is directly proportional to the average kinetic energy of the particles. And so here I'm not getting the answer. Can the kinetic energy of object be negative? And think about how kinetic energy is calculated. And then actually average kinetic energy is related to the Kelvin temperature. And the Kelvin degree temperature is also referred to an absolute temperature. So absolute temperature, people use that very often, because in some other cultures, some countries, they don't want to honor Kelvin, but they just want, international, there's a temperature, people just call them absolute temperature, or about a degree is called Kelvin, how many degree Kelvin, and also it's called a thermodynamics temperature, and that's so that's directly, these temperatures are directly related to the kinetic energy. Of course, we can have some other temperature scale, like Fahrenheit, that's what we daily use in our normal life, and also Celsius temperature, that you can have a conversion between the absolute temperature and Kelvin temperature. But now we are dealing with physics. So absolute temperature, thermodynamics temperature, or Kelvin degree temperature, they all referring to the same temperature, which is actually directly proportional to the average kinetic energy of the particles. So once again, here's the video finish, and then there's a video talking about how do you use Excel to process data. All right, if you have a question, we can have a Zoom meeting, or we can answer your question in next class. Bye bye for now.